Okay, so the end of chapter 22, we're just first going to go back over aromatic compounds, so compounds that contain a benzene ring, and go into a little bit more detail in a couple of parts. So a bit of revision from chapter 21, we looked at benzene, methylbenzene and ethylbenzene. So we have our benzene structure here that we'll revise in a second. Methylbenzene is the benzene ring with a methyl group on. And ethylbenzene then is the benzene ring with an ethyl group attached. You need to be able to draw those. So each carbon atom has 4 electrons in its outer shell. We can see 3 electrons are used up in these 3 bonds, 1 to hydrogen and 2 to the adjacent carbon. The 4th electron, just to mention, there are 3 sigma bonds. The 4th electron in each of these carbon atoms is in the p orbital if you were to write out the electron configuration. So each carbon has a p orbital that has 1 electron in it. Those p orbitals are all arranged parallel to each other all around the hexagonal shape. And each electron in them, what we would assume to happen is that there would be overlap of adjacent orbitals, so 2 orbitals next to each other would overlap, and they would share their 2 electrons in order to complete the 4 bonds that carbon needs. So you can see that here, that would lead to 3 double bonds. The only thing is there's a second option, so that you could have these 2 carbons and these 2 carbons. So in the beginning we saw these 2 in front here overlap. So there's a second option there. There's 2 ways that these double bonds could form. So the way that it's written out here now, or if you were to place a double bond here, here and here as it's just changed to. In reality, neither one of these happens. In fact, all 6 orbitals are going to combine and the 6 electrons within them are going to be delocalized. So you get a formation of this donut-shaped ring up above the carbon plane and a donut-shaped ring below the carbon plane. So it's a donut-shaped electron cloud. So it's an electron cloud, one above the carbon plane, one below, and we call it a pi bonding system. The electrons don't belong to any one particular carbon. They help to bind all 6 of them together. And what we notice here is that benzene is a planar molecule. All of the atoms lie on one plane, and you have the electron cloud above and below that. It's a particularly stable configuration because there's no particular double bond there to undergo addition reactions like the alkenes did with the bromine water and the acidified potassium permanganate. So the next couple of slides are just the key points and kind of going over that again. So if you feel you need that, I'm just going to flick through them here. You can pause and read and take any notes that you might need. So the physical properties then of benzene, methylbenzene and ethylbenzene, they are liquids, they're insoluble in water. They're non-polar, so they're insoluble in polar water, but they are soluble in non-polar solvents like cyclohexane. The uses of methylbenzene, as we know, methylbenzene is used in favor of benzene because benzene is toxic and carcinogenic. So methylbenzene is used as an industrial solvent instead of benzene. It's used in the manufacture of plastics and explosives, and it can be added to petrol to increase the octane number. So those are some aromatic compounds, but in fact there are millions of aromatic compounds. It's a whole branch of chemistry where we study compounds with benzene rings in them. So examples include pharmaceutical compounds, herbicides, insecticides, detergents, dyes. You can see a lot of these examples just to see the structure of them on page 403. I'd recommend you have a look at that. And one particular example that you need to know about is acid-base indicators. So we've used phenolphthalein and methyl orange in the lab quite a bit, and you can see here in phenolphthalein we've 2 benzene rings, and the same in methyl orange, it has benzene rings in there as well. So that's a particular example to note that they might ask you about. On to the final part of this chapter then is organic natural compounds. So as the name might suggest, they're natural organic compounds, are compounds that are found occurring in nature. There's a list of examples here. So for example, almonds, you can extract benzaldehyde from them. Coffee, you can extract caffeine from it. And so what we're going to do in this section now is to look at how that happens. And the example we're going to look at is extracting eugenol or clove oil from cloves. And the way that we do that, the method is steam distillation. So you might have used distillation, or you will have heard of distillation in junior cert. And this is a particular type of distillation using steam. So it's used to separate oils from their plant sources. So it's a separation process to isolate compounds at temperatures below their decomposition temperatures. That's very important. So if you were to do normal distillation or just try to extract the oil by heating up the plant, then you would end up with a temperature that's too high and it would cause the plant and the oils to decompose. And it's carried out by bubbling steam through the plant material and distilling off the immiscible liquids. So it's used to collect oils because oil and water, which is what steam is, are immiscible. They don't mix together. You might see that at home if you try to put a bit of oil in with some water, it'll just sit on top. So again, the main purpose here is to avoid temperatures that are too high, as a high temperature may destroy the plant material. So steam is passed through the plant material and that's going to release oil from the plant. The mixture of oil and steam is then passed through a Liebig condenser. Hopefully you recognize that. The two liquids are immiscible, so when they're collected, when both of them are condensed, they don't mix together, so the oil floats to the top. And if you want to pause and read there, that's basically just breaking down what it says in the green box. This is your apparatus. So you've got a steam generator. That's where you put your water into. You're going to heat up your water so that you're producing some steam, some gas. We have a safety tube in here, and it's very important that you know why that's there. And the reason it's there is to prevent a buildup of pressure formed by the steam in the steam generator. So obviously this is a liquid, we're turning it into a gas, so that's going to increase the pressure. So the safety tube is there to release that. The second important thing is that you'll notice it's under the level of the water, and you really need to make a note of that. It has to be below the level of the water, so that the steam doesn't just simply escape through the tube. You want the steam to carry on into the rest of the apparatus, so you want to make sure that the tube is under the water. It will still relieve the pressure, but it won't allow the steam to escape. We want all of this to be airtight. The steam then, so we're evaporating the water, the steam travels first into the steam trap. That's there to collect steam that has condensed back to water. And the reason we want to keep that water in here is that we don't want too much of it going into the flask containing our plant material, because we don't want that to fill up with water too quickly. So we get our steam passing in here. Anything that has condensed already will stay there. Other than that, the steam will continue through the glass tubing, and it will come down and it will be bubbled in here into the cloves. The important thing to note about the cloves is that we use whole cloves, not ones that have been ground up into a powder. There's two reasons for that. The main one that you need to know is that there's just more oil in the whole cloves rather than the powder. The second thing as well is if there's a powder in here and there's gas bubbling through it, that's going to mix up some of the powder, and you could get some stuck up in the tube here, which wouldn't be ideal, or you could get some stuck up above the level of the water, whereas that's not really going to happen with the whole cloves. They're not going to float up. Then the steam is bubbled through here. That's going to liberate the oil. The oil is going to, the steam is going to heat this up. The oil will evaporate in here as well, And then the steam and oil, some steam and oil, will pass through the Liebig condenser, which is the cold water running through it. It's going to cool it down and turn them back into a liquid. And here at the end, we'll have a flask that's going to collect the clove oil and the water. And that's called an emulsion of clove oil and water. We'll get to emulsion in a second. So again, these 3 points in black here are just the 3 things that I said you needed to note. And as I mentioned before, the main constituent of the oil is called eugenol. You do need to know that, that's very important. And its uses are that it's used in food flavorings and it can be used to treat toothaches. So emulsion, as promised, an emulsion is a dispersion of small droplets of one liquid in another liquid in which it is not soluble. So in our example, we have small droplets of oil in water and the oil is not soluble in the water. So now we need to find a way to remove the water and obviously extract the oil. So there's a couple of steps to this. The first one is that you need an organic solvent to be added. That's going to dissolve the oil so that we're separating the oil from the water. Again, cyclohexane is non-polar, water is polar, so they're immiscible as well. They're not going to mix. This is then separated and the solvent is allowed to evaporate. So the cyclohexane is going to remove the oil from the water. Then we just heat it up to evaporate the cyclohexane and we'll be left with our oil. This process is called solvent extraction or liquid-liquid extraction. This is your green box detailing that to you there if you want to pause and have a read. So just to go through the steps for this, you add cyclohexane and the emulsion in a separating funnel. And what you'll get is you'll get 2 layers. You'll get the aqueous water layer and you'll get the organic layer. Now, something I forgot to mention earlier actually is that the emulsion that you get is going, and this is important, so please note this down, the emulsion that you get is going to be a cloudy liquid. So you'll have the water in there and the cloudiness will be coming from the oil mixed in with it, the drops of oil in the emulsion. Okay, so back to this. You add the cyclohexane and the emulsion to a separating funnel. You put a stopper in the top of the funnel, take it off of the clamp, and you invert it and shake it 10 times, roughly around 10, in order to mix them together. For safety, an important feature here, so put a little star next to this for yourself, before you re-clamp it again, you keep it turned upside down so that nothing's going to come out, and you open the tap here. The tap is open to release the pressure that has built up from you shaking the funnel. You're then going to clamp it, and the aqueous layer, the water layer, is going to be on bottom, and the organic layer or the non-polar layer is going to be on top. So this is where your oil is going to be. So we release the aqueous layer into a beaker and then we're going to collect the organic layer in a conical flask. So we're collecting our organic layer over here. Now, doing this once isn't going to get all of the oil out of the water. Remember, it's droplets of oil are spread throughout the water. So we're going to repeat that process of mixing it up with more cyclohexane 2 times to extract the maximum amount of oil possible. So you're going to repeat these steps 2 more times, so 3 times in total to get the maximum amount. Each time the aqueous layer should be less milky in colour. So again, like I said, that cloudy colour should be there in the beginning. And as you remove the oil, the water layer, the aqueous layer should become clearer and clearer. In order to get rid of the water, we need a drying agent that we're going to use, which is magnesium sulfate. It will go into the mixture and it will remove any water present by forming clumps with the water. So we add it in small amounts until the powder settles at the bottom of the flask. That will indicate that no water remains. If it doesn't start clumping up, if it just falls straight to the bottom, no water is left. We then find the mass of a clean, empty conical flask. We filter the organic layer from our initial conical flask to remove the hydrated magnesium sulfate. We rinse out the original conical flask and the residue with cyclohexane to ensure all of the oil is transferred. We place the conical flask in a water bath in the fume cupboard to evaporate off the cyclohexane. The reason we put it in a water bath in the fume cupboard is because cyclohexane is very volatile. If we were to use a hot plate or a Bunsen burner, it would also cause the oil to be evaporated off as well. It would heat up the oil and evaporate that off too. We then find the new mass of the conical flask, and by subtracting the mass of the conical flask from that, we can get the mass of the oil.